Hello, hello, good morning, everyone. Thank you for joining us. Welcome. I'm seeing the number of attendees are rising very fast, so I give it a few minutes, maybe a minute or two, to just make sure that we have enough people in the room. Okay, let's just start. Good morning, all. Thank you very much for attending our latest technology talk, BEPA Technology Talk, talking about the sodium-ion batteries. My name is Bozor Khambai. I'm the Executive Director of BEPA, Batteries European Partnership Association. Just a few words about us. We are the we have been and are the private side of the BAT4U partnership with the European Commission, defining the R&I priorities and funding priorities for the battery ecosystem research and innovation. If you're a BEPA member, you know that you are in the front seat of developing the calls and developing the text of the Horizon Europe work programs. That experience, of course, entails a lot of adjacent activities in making sure that the network of the stakeholders are well fit toward the unique goal of making this European battery value chain competitive and sustainable in the long term. In the long term, so please have a visit to our website if you would like to know more about us. We have a lot of webinars monthly and weekly. We have our flagship event, Battery Innovation Days, coming up in Graz in early December. Please feel free if you would like to join us there and know more about the European projects and the European battery ecosystem in general. And of course, we are having dedicated activities on the European battery policy, European innovation policy for the batteries, and we have a dedicated streamline of activities for the battery startups in the field. So we, to that point, we're going to talk to one of them, one of the first, I think, battery startups in Europe working on the sodium-ion battery, this very promising technology that has made a lot of waves in the ecosystem for the past few years. There has been ups and downs, just like any other chemistries in Europe. But we start with two of the colleagues from this startup called Altris, the Swedish startup focusing on the sodium-ion batteries. We're gonna hear about the science of the sodium ion a little bit from Reza Younesi. Reza is the professor at the Uppsala University, the founder of Altris, and one of the pioneers in research on this specific technology. So Reza needs a little bit of introduction. And Johan Lundberg. Johan is the head of strategy and corporate development at Altris. So I keep my talking short and give the floor to Reza to give us more information about the latest progress in the research on the sodium-ion batteries, and then Johan on more information about the Altris itself. So please, Reza, the floor is yours. If you would like to share your screen, please feel free. You
Do you
are,
see the slides?
yes, I can
Very
see
good.
your slides. Yes.
Excellent.
All
Thank you
good.
very much, Bozorg, for the nice introduction, and thank you to you and everyone at BEPA for having me and Johan for this seminar or webinar. Very happy to be here, and thank you to everyone. There are like more than 180 people, almost 190 people in this webinar, which is quite interesting. And thank you to everyone for taking your time to join this webinar and to listen to our presentation. So I'm gonna spend a few minutes giving a little bit introduction to the field and what I have witnessed in last few years about how the assessments about battery technologies and different battery chemistries went wrong in Europe. So to provide you a little bit feedback and insight about battery industry, and at least provide some feedback about uh, how I think we could make Europe stronger when it comes to batteries. But I'll also spend some slides talking about chemistry and electrochemistry of batteries, and I hope you don't mind, because I heard that there are like there's a wide range of competence and experience in this webinar. People have some chemistry and electrochemistry background, and some people are from policy and industrialization. So to start, let me see if the slides work. Yes. So as I mentioned, I'm going to give a few examples of what I call it incomplete assessments in Europe that has happened in the last 15 years to see what we can learn from these examples to do a better job in the future. The first one is this statement that there is enough raw materials for lithium-ion batteries, which today probably everyone agrees that this is not necessarily 100% correct. We need to be careful when we say that, and then we need to make sure that there is enough raw materials for lithium-ion batteries. But if you go back 15 years ago, believe me, this was a statement by some policymakers that they were saying that there will be enough raw materials for lithium-ion batteries. As soon as lithium-ion battery industry moves forward, then mining industry also moves forward, and then we will have enough materials. We don't need any other materials. We don't need any other chemistry. Today, we know that the lithium-ion battery production has expanded a lot over the last few years. So China has been leading this industry and will most likely lead this industry in upcoming years. But it is expected that Europe and US also will catch up with battery production. So it's a huge number. 4,700 gigawatt hour cell production is huge. And just to put this in the context, probably you have heard about Northvolt in Sweden, which unfortunately didn't work at the end. Northvolt aimed for 32 gigawatt hour factory in northern part of Sweden. So if we're going to really reach this amount of cell production by 2030, we will need around 120 to 150 Northvolt type of gigafactories around the world. And you have learned by now that how difficult it was to have even one factory called Northvolt in Sweden and in northern part of Europe. Now imagine we need 120 to 150 of those factories around the world. So it is a big challenge, which requires also lots of materials to go into these factories. So today it's very clear that there is a big gap between supply chain, between supply of these elements and the demand that we will see in upcoming years. And remember, this is not only about cobalt and nickel, but also we see a big gap for lithium, for natural graphite and synthetic graphite. So this is the first example. I just wanted to highlight that if you go back 10, 15 years ago, people were saying that there is enough material for lithium-ion batteries. And today we see that this was a wrong assessment back in those days. Another one that I have seen a lot of people were saying, if again, around 10, 15 years ago, that LFP batteries are not good enough really, because the energy density is not that high. And if you're going to spend lots of money to have a gigafactories, then we should produce the highest energy density possible. Then people have been talking about solid state batteries, about high nickel cathodes, etc. And other chemistries, lithium sulfur, lithium oxygen, lithium metal based batteries, and so on. And again, all those technologies are definitely very interesting in terms of chemistry and electrochemistry and science, but they were not ready for industrialization. What was ready and rather easy was LFP, if you go back 10, 15 years ago. And for number of reasons, European industry, including automotive industry, didn't want to pay attention to LFP back in those days. I had a project with two major automotive industry where they said, no, LFP is not good enough for us. In Europe, we are premium. So that was a big mistake that we have learned today. And now everyone is after LFP in Europe, which is not necessarily good timing. It was good timing 10, 15 years ago. I have seen also that people have put high energy density lithium-ion batteries, NMC-based batteries, in containers for stationary storage. This is also very wrong way of using batteries. And this was done because there was no LFP batteries in Europe if you go back 10, 15 years ago. So people were using NMC-based for stationary storage for a small project in a stationary storage sector. But what we know today is that this is probably correct, that we need to diversify chemistries used in batteries. So you would go for high energy density batteries for some applications like portable devices and some premium EVs, but you don't need to have high energy density cells for other applications. And actually, you should not use those nickel-based, cobalt-based materials for stationary storage. It doesn't make sense in terms of sustainability and also in terms of access to raw material. Another interesting example that I have seen in the last few years, that people say that sodium-ion batteries are not good enough, which is kind of same mistake that people made in Europe about LFP around 10, 15 years ago. And some people are doing the same mistake today. And the argument here is that sometimes people try to compare sodium-ion batteries with LFP batteries and say that, okay, which one makes more sense? While this is not actually the correct way of thinking. But the point here is that each of these chemistries have their own niche, and we need both of them. It's not that one chemistry is going to replace the other one. So, of course, any new chemistry, whether it's sodium, potassium, calcium, magnesium, whatever, you need to show them they make sense in terms of dollar per kilowatt hour. So there is some competitiveness. So they are not, let's say, they are not 5 times or 10 times more expensive than lithium-ion batteries. Otherwise, there is no market. So there has to be some competitiveness. But there are other factors that could play a much more important role than only price. So when it comes to sodium-ion batteries, resilience and security of supply chain is a big thing that will work in favor of sodium-ion batteries versus many lithium-ion batteries. So it's not that everything is about cost and cost. Then there are some advantages also with sodium-ion batteries, like zero charge storage, which could be a big thing for transporting cells and shipping cells around the board. And also high power, lower cost, and possibility of having aqueous-based electrode coating and for sodium-ion batteries that will work in favor of sodium chemistry. And if you don't believe me by now, you could perhaps listen to the interview of CATL CEO a few months ago, where he himself said that sodium-ion batteries will take a significant portion of LFP market in the future. So it's interesting again to see that China has understood this, and they are ahead, and they are moving forward very quickly with sodium-ion batteries also. While they have the market for LFP, but still they don't stop there, and they are expanding to sodium-ion batteries. And then we are doing a little bit slow in Europe, so we need to move faster. So with this introduction, I hope I tried to set the scene for the research activities that we have been doing at Uppsala University, mainly around sodium-ion batteries, but also a little bit other chemistries like potassium and magnesium. So what I'm going to cover here is the major activities in my team at Uppsala University, which is developing new materials for those new chemistries, using in-house and synchrotron-based characterization tools to understand aging in batteries, and then Altris as a spin-off from Uppsala University that we launched in 2016, 2017. So the first topic to cover is about solid electrolyte interface, or SEI, which probably most of you know is very critical component in the cell to make the cell kinetically stable. The reason is that the negative electrode, the electrochemical potential of the negative electrode is beyond the stability of electrolytes. So we need to make these thermodynamically unstable system somehow kinetically stable. and that is done by forming SCI. So you probably know that there are few requirements from SCI, like ion diffusion, etc. But one thing which is a little bit neglected in literature is just chemical stability and dissolution of SCI. So this is what we have been trying to understand in sodium-ion batteries and see how different that is compared to lithium-ion batteries. So what you see on the left is a model system that we have been using to evaluate different electrolyte chemistry. So you have a working electrode, which could be a foil, like a platinum foil or gold foil, or it could be a glassy carbon. So there is no intercalation into this electrode. So the reason that we are using this type of model system is that just to simplify the aging mechanism and to understand each aging mechanism one by one. Because if you look at the picture on the right, as you see, there are many different aging mechanisms in a real lithium-ion or sodium-ion batteries. So it's very difficult to identify each and quantify each one by one. So what we try to do here is on the left is to mimic this different condition in the cell and try to understand SCI formation and dissolution. So as you see here, what we do, we form SCI on the working electrode, then we apply some relaxation or pause time where there is no current or potential applied during this relaxation time. And then we can measure the amount of SCI dissolved during this relaxation time, and that gives us information about the stability of SCI in a specific electrolyte solution. So what we have found so far is that if you do this type of galvanostatic cycling and give different relaxation or pause time, as you see in the figure top left, then you can measure the capacity loss during this relaxation. And if you plot the capacity loss versus the square root of pause time, as you see in bottom left, then you can see that there is a linear relation between these two parameters, which indicates that this aging mechanism is diffusion-based phenomenon, and it is kind of confirming that it is SCI dissolution, which is diffusion-based, leading to this capacity loss. If you plot the capacity loss versus the volume of the electrolyte, as you see in the figure on the right, then you can see that then there is again a linear relation, which again indicates that the higher the volume of the electrolyte, the higher the capacity loss due to SCI dissolution is, which again confirms that this is diffusion-based phenomenon. So we have used this method basically to evaluate different electrolyte chemistries. And the one you see on the right, these are just few examples. And I'm not saying that these are the best electrolyte necessarily for sodium-ion batteries, but these are just few examples that we have tried to evaluate for sodium-ion batteries using this methodology. So with this, I would like to move to next part of my presentation, which is about development of battery materials that we have been working at Uppsala University. The first example is sodium bob salt, which was first actually demonstrated. The synthesis of this salt was demonstrated by Stanley Whittingham a few years back. But this salt is not soluble, or the solubility is very low in common solvents like carbonates and ethers. So no one paid really any attention to this salt because you couldn't dissolve it in carbonates and ethers. But then what we found, you can dissolve this salt in alkyl phosphate solvents like TEP and TMP, which gives you a non-flammable fluorine-free electrolytes. So very interesting that you can make batteries potentially safer and more sustainable by excluding fluorine from the electrolyte chemistry. The conductivity is not that high, for sure lower than carbonate-based electrolyte. You get around 5 millisiemens per centimeter at room temperature. So it's not impressive conductivity, but it's not too bad. You can easily achieve C over 3, C over 2, and even 1C in big multi-layer pulses, as we have demonstrated at Altris. The issue with this electrolyte, however, is that the first cycle Coulombic efficiency is low. As you see, you lose around 20% capacity on the first cycle if you use this electrolyte as it is without any modification. And then what you see in the figure top right, there is a small shoulder around 1.7. That is where sodium bob is decomposed. And the composition products are very soluble in the electrolyte, which means that there is no passive layer formed to form an SCI, efficient SCI. So what we could do here, we could play with the formation protocol to optimize the first cycle, as we have shown in one of our studies that you see down um, in the note. The other possibility is to optimize the electrolyte by different additives. A common practice that you try to make the SCI formation more efficient when the electrolyte itself is not very efficient to form SCI. So here we have evaluated a number of different additives, and then what you see on the right, we have enabled sodium bob in TP electrolyte to cycle for almost 1,000 cycles with 65% capacity retention. And this is like a multi-layer um, um, cells based on Prussian white and hard carbon that we have evaluated here. The next and the last example is Prussian white, which is the core business for Altris. The reason that we were interested to this material back in 2015 with my PhD student, former PhD student Ronnie Mogensen and colleague William Brand was that it's interesting material in terms of capacity voltage, but also you get two flat plateaus, kind of similar to LFP. So we were thinking to use this material actually as a stable counter electrode or a stable reference electrode when we study SCI dissolution. So we never aimed to commercialize this material, but we started to see how we can synthesize this material in the lab to use it for other studies. Then we ran into this paper by John Goodenough, which is an interesting paper to show the material. But the synthesis method in this paper is very complicated and not really scalable. Then we try to scale this the material and synthesize. In the beginning, we just try to upscale it from a very small scale to 0.25 liter and to 2 liter, just to have more material for our studies. But we found that actually we can easily do that, and it works. There are, of course, a number of details, but we could produce interestingly high quality Prussian white. Then at some point around 10 liter, we decided to leave the university and take this as under a company called Altris, which was officially launched in 2017. So since then, Altris has shown this cathode material combined with different anodes, including hard carbon in different scales, from coin cell to a small 1 to 2 amp hour multi-layer pouch cells to big multi-layer pouch cells up to 40 amp hour, which Johan will talk about it much better than me about what Altris is doing today. But with this, I'm going to conclude this presentation with two messages that, yeah, it is today clear that we need local production of batteries. And this is not only battery cells, that is very clear to everyone that we need to have cell production in Europe, but also material production. We need to cover the whole value chain. It will take time. It's not easy, but we need to do that in long term. And then we need to focus on materials that are available and abundant in Europe. That doesn't mean that those chemistries like sodium chemistry will be used in every single applications. No, but it is clear that we need those type of batteries to produce in Europe. Just in terms of sustainability, resilience, and security of supply chain, we need to work on those batteries. And the good thing by diversifying battery chemistries is that we will decrease the pressure on lithium-ion batteries also, which is definitely interesting and important for applications where high energy density is needed. So let's work together for hopefully having accurate or more accurate assessments in the future, so we don't repeat the same mistakes as it has happened in Europe around 10-15 years ago. So I would like to thank the students and postdocs at Uppsala University who are behind these activities, and also the funding agencies and industrial collaborators who have invested in Altris. And yeah, thank you to you all for listening to this presentation.
Thank you very much, Reza. Thank you for your message. It was really also, it actually very much resonates with the message that from the BEPA side we have for the policymakers, and it's specifically European Commission. As you mentioned, the diversity matters. We have to diversify our chemistries, our technologies for this diversified actually modes of mobility and broader electrification at the continent level. This is not a one chemistry for all. There is not a single solution. We have to diversify, as you mentioned, not necessarily cost, but other externalities that are imposed. Very much share that, and specifically your point about the consideration of the entirety of the value chain. That's extremely important. That as you mentioned has been very much overlooked in the past years. Uh, it's not necessarily a business development and a business plan that the supply and the midstream and the downstream should be connected. It's also valid technically. We cannot develop the batteries in isolation without knowing the sources, without having the localization of the development and engagement between different parts and different stakeholders in the value chain. So thank you very much. Just before we go to Johan, just please stay with us, Reza. We will have Q&A after that. So thanks again. Before we go to Johan, I want to flag a couple of information. Speaking of the sodium ion RNI, just update you if you're non-BEPA member about the funding that is coming up for these specific technologies. So we have already funded a few projects on the sodium ion. We have intensified that activity in the next year. So in 2025, we will have a 24 million call for the chemistries, for what we call design to cost chemistries for mobility. Specifically, sodium ion is in that short list of with LFP and LFMP. Again, to the point of Reza, sodium provides a very good alternative to LFP. As we know, there is very little control of the Europeans on the supply chain and the development process. So the deadline for that is January. It's a little bit late maybe to start now, but just to give you a heads up, for the 2026 and 2027, we will have 7.5 million on the bio-based material, developing battery grade material from bio-based material. Probably a lot of projects will be focused on hard carbon, which is the anode of choice for the sodium ion batteries. We will have a 40 million call in 2027 on the battery cell manufacturing, and that specifically focuses on lithium ion and sodium ion batteries. So that has been identified in the call. As we know, the production shares almost all processes. So that's a technical advantage and leverage that sodium ion has in the commercialization. And a 50 million on the direct recycling in a few years will be opened up. The issue that has been raised from time to time regarding this kind of a low value material like LFP, like sodium ion, is that the recycling may not be economically feasible. That should be addressed through innovation. That should be addressed through research. We need to reinforce the activities on the direct recycling, on the shorter routes for the recycling, and that's very much in our agenda and will be funded in the coming years. Okay, thank you very much. I give the floor to Johan to give us more information about the startup Altris itself. So please, Johan, the floor is yours.
Thank you very much, and thank you, Reza. I will touch upon some similar topics like Reza, but I will address mainly two things. The current state of the sodium ion market and how Altris as a company we navigate those trends in the market. So starting off with just a snapshot of the recent trends. For those of you in this call, I assume that you follow the market, so this will not be news to you. But during the last 1 or 2 years, there is a significant overcapacity being built out in China, all throughout the value chain, all the way from raw materials down to cells and systems. This is pushing prices down in a non-sustainable way, and it's creating effects all throughout the world. At the same time, there is a slowing electrification rate. We don't see as aggressive market shares of EVs as was expected a couple of years ago. There is a turbulent geopolitics that is shaping the market as well, with tariffs and production incentives that gets switched on and off on a whim. We see that LFP is moving more aggressively than anticipated in more segments in the EV sector, not just budget cars, but also in the mid segment. And here China has a big advantage, and all the non-Chinese players are playing catch up at the moment, trying to pivot to LFP from NMC and other chemistries. And these are not new, the trends. What is new is the effect that this has had on the Western battery market. We all know about Northvolt, but they are not alone. We have companies like Custom Cells, Porsche's Cellforce, Natron Energy in the US recently filed for bankruptcy as well, all affected by these trends, and also the reduced investor appetite that comes with these market trends. So US and Europe's battery market is in a tough position right now, but we are definitely pulling through and seeing the light in the end of the tunnel come next year. And more
Apologies, Johan. Sorry for interruption. If you are moving your slides, we cannot see that unless you are still
Are you
on
still
the first
on
one.
the?
Yes, we are still on the first slide.
Okay, the only Altris.
Yeah.
Okay, that's weird.
And I think your image is now frozen, but okay, I think Johan might be disconnected or having connection issues. Okay.
I can call him to see what happened.
Yes, it's okay. I mean, before he comes up, maybe I can ask you a couple of questions, Reza, so we are efficient with time. About the TRL, this is something that sometimes in the general battery landscape, sometimes this number or this figure sounds artificial. But what's your general take about the TRL? How would you classify also based on the different chemistries within the sodium ion portfolio, the Prussian blue and white, the polyanionic, and also the layered material? Could you give us a short description of your insights about the
Good question.
elements?
If you think about sodium-ion batteries in general, as probably everyone here knows, that there are commercial sodium-ion batteries produced in China, commercial cells, commercial packs today. So no one is, let's say, worried about a possibility of producing sodium-ion batteries in commercial scale, compared to if I go back 2017, to be honest, when we started Altris, many people never believed that, and many people didn't want even to consider sodium-ion batteries for a number of reasons. But today it is high TRL product, which again, you don't need to believe me. You can just listen to the interview by CATL CEO. So it is happening in China, and there are a number of projects outside Asia that also that are based on sodium-ion batteries, but those cells are coming from China. Then if you go a specific chemistry, then what I have seen is that all these different chemistries that we are talking, oxides, Prussian blue analogs, etc., they have been used in commercial cells. So different companies have different product. So I don't see any issue in terms of TRL of those active materials as you see commercial cells. What I would like to highlight here is that, especially for Europe and US, sodium-ion batteries, when we talk about sodium-ion batteries, the other factors, in addition to dollar per kilowatt hour, other factors like sustainability, security of supply chain, and resilience are extremely important for sodium-ion batteries. Then there if you're gonna use nickel or cobalt or those elements that are not abundant, that is a big challenge for sodium-ion batteries. I would say that I don't see. Well, let's put it like this: I don't see any point of using nickel or cobalt for sodium-ion batteries, because then again, it is against the purpose. I mean, you are working with sodium-ion batteries to have security of supply chain, local production, local material. Then if you're going to import materials from outside your region, whether it's called Europe or US, then what is the point? So. You are mute, Bozorg.
Yeah, I mean, so the point is not necessarily making it work because there is the active material or the redox agent is sodium. It's just that the entirety of the materials encompassing the cell should follow that goal. Great. I hope Johan can hear us.
Yes, I'm
okay.
back.
Okay.
I've joined in the browser now. Hopefully it works.
Yes, and I can share the slides if you would like me to.
Please go. Please do. So you can go to slide, the third slide. That one, yes. Thank you.
Okay, please.
Yeah, so I'll pick up where I think I left you. So talking about the specific market sentiment around sodium ion, which has historically, it has a lot has had to do with price and being cheaper than LFP and lithium in general. And sort of around the first hype cycle of sodium ion around 2023, where Northvolt, for example, announced that they were moving into sodium ion. Around the world, there was over 300 gigawatt hours of sodium ion capacity announced in that year alone. And the lithium prices were at record highs at that point. So the questions from customers were really, how much cheaper is sodium ion? How much can we save on a cost per kilowatt hour basis? Since then, the lithium carbonate prices has dropped a lot. We're seeing some signs that it recovers. It's up from the very bottom quite much, but still on low levels compared to a few years ago. That said, the market is picking up interest, I would say. And as Reza mentioned, CATL revealed their next generation sodium-ion battery this spring. And their CEO claimed that over time, 50% of LFP can be replaced by sodium-ion. This is a very, of course, bullish statement, but it shows the confidence that CATL has in the technology and the promise that the chemistry has. So really now, even though the prices of LFP is so low, there is still interest. And what the customers want to know now is what sodium ion can do that LFP cannot do, even if the price is the same or even a bit higher. And can go to the next slide. And this is where then Altris comes into the picture. Altris, as introduced by Reza, a CAM manufacturer developing technology based on Prussian white chemistry. So we are primarily a cathode active material player. We are moving a little bit into battery cell development as well. We're doing that to ensure that the customers can basically industrialize our technology, because the market is quite immature at the moment. So we need to do joint development projects together with the customers to ensure industrialization. We have a robust patent family. We are developing together with our strategic customers and investors, which are Clarius, Maersk, and Volvo. We are developing two different types of applications, one power-focused and one energy-focused. And the target markets that we aim for are low-voltage batteries, defense applications, ESS, and maritime applications. And those customer markets are selected based on the product market fit for those. It's not only price and it's not only energy density that matters for this. And this is where sodium ion really shines. So if you go to the next slide. Here are the sort of rationale for why these market segments make sense at this point in time. So for low voltage customers, there is a lot of emphasis on the power capabilities. Right now, a lot of the market is being held by lead acid, an old, very old technology with very high power capabilities, but it's going at some point going to be phased out, and here we see sodium ion as a prime candidate for that. Also, low temperature performance is super important here. We have a wider temperature window of operations. We can operate all the way down to -25 degrees Celsius, something that LFP cannot. And on the defense customers, of course, the supply chain autonomy is critical. It's a must-have with European supply chain, something that can be achieved. Full non-China supply chain possible already today with a full European supply chain, clear visibility on how to achieve that if some of the critical components are being industrialized as promised. Also here, cold weather performance and 0-volt storage, important thing for the defense segment. This is because we're using aluminum on both electrodes, so we can discharge the battery all the way down to 0-volt, which gives a lot of benefits when you store it and when you transport it and when you install it in a system from a safety and cost perspective. And on the ESS market, disregarding the promise of lower price, there can be system-level savings by improving the round-trip efficiency. And here also is because we can go down to 0-volt, and we can go all the way up to 100% state of charge without damaging the battery. So there's a bigger chunk of the energy is getting used, basically. And also, you can save on system levels on cooling. We don't have as high risk of thermal runaway. It's not required than the advanced cooling systems, etc. That gets, it adds to the cost of storage, basically. And for maritime, it's super important with safety. A thermal runaway event out at sea would be not good. And so the fact that we have a better safety profile and much less risk of thermal runaway is very interesting for the maritime segment. So all of these things gives us an edge versus other technologies in these markets, and hence why we focus on it. Next slide, please. And given the recent developments with, as we saw with Northvolt, for example, and how difficult it is to scale manufacturing, we have chosen a very focused strategy when it comes to vertical integration. We want to focus on the things that we are good at, so active material development, and the growth will happen through strategic partnerships, both upstream and downstream. So partnering with the chemical producers, primarily sodium cyanide, which is the biggest part of our bill of materials, utilizing the existing infrastructure there and the way that they are handling waste and so on, gives a lot of benefits. And also on the downstream side, where there is a lot of capacity in the world and in Europe being built out for lithium-ion production. And here we can use the same equipment as LFP if we want to produce our battery cells. And then we do the final product development together with the end customer. And here our primary paths now are with Clarius, Maersk, and Volvo, also our investors. You can go to next, and I think you can skip this one in the interest of time and go to the last one. So summarizing, except for being a cheaper material, why is sodium ion needed for Europe? It's 3 points on industry localization. It's possible to localize it entirely in Europe and other markets as well, should be said, like the US or India, for example, if you want to go ahead and localize it fully. It's not possible with lithium, or it's very difficult at least. And sustainability, environmental, social, and governance risks are much lower due to the fact that we can source it from known entities in nearby countries. And also on the CO2 emissions. And here I want to emphasize that these are theoretical numbers, but in theory, the best-in-class lithium producers in Europe could reach as low as 10 kilograms per kilowatt hour in 2030, whereas we have a LCA model that shows all the way down to 4. And here the biggest drivers of that are lower, more efficient production processes. For example, in the cathode production process, we never go above 100 degrees in any calcination process, whereas for NMC or other sodium-ion technologies, they go all the way up to 700 degrees, for example, saving a lot of costs and emissions. I think I'll stop there, and we can open up for some Q&A. I see that there's a lot of questions in the chat.
Yes, thank you so much, Johan. Thank you. That was really interesting to see your journey in detail. Maybe one question from my side, and then I will present the questions asking the Q&A. So, given that the ecosystem at the moment is a little bit turbulent, to say the least. I'm sure you have had a lot of experiences with the downstream and integrators, different applications. As you mentioned, there's a huge potential for a diverse set of applications for sodium ion. Maybe if you could give us a little bit of insights about your experience in general with different applications, how to accommodate that. First, is there a good realization of the potential of this technology, and then talking to them, do you need to going back to the development and the upstream sector of your own company? Do you need to do a lot of adjustments to meet that, or there is kind of a general standardization mood?
That's a good question.
For the sectors who use batteries, yes.
Yeah, so we do, for the customers we do some co-development on the cell level. What's good about our technology is that the cathode material is the same. So we can use the same CAM for many different applications, and the difference in performance will come on the cell design level. So that's a big thing for us, being able to use our material in many different applications, and it's a very robust chemistry. So you can use it, in many different scenarios.
Thank you. So a broader question, maybe from Reza or Johan yourself, on the manufacturing. I made a rather confident statement in the middle that the majority of the production is shared with the lithium-ion batteries, and that's an advantage. But maybe I was a little bit too confident. Just to double check that with you, what do you think? Is that the case? Are there kind of a processes that could give a kind of a technological leverage to the sodium ion, or vice versa? What we need to develop? I mean, that's maybe one of the biggest questions for us in terms of the processes. We know that also. Sorry, I'm just giving you a line of questions, but please feel free to pick whichever you want. But the techno-economics of the sodium ion battery is a little bit overlooked. Usually the focus is on the cost of the materials, but we know that with some trade-offs, if you will, in the processes, in the synthesis, we can go to a kind of a final product being more economic and cost-effective. So, what's your take in general about the manufacturing? What are the differences? What are the similarities? How we can improve?
Yeah. I'll pick up on one of the early questions in that line of questioning. So we can use the same equipment as LFP in our pilot facility that we have in Uppsala. We are using standard lithium-ion equipment. It's nothing bespoke. So we're making large format cells on a full industrial line here. there is for LFP at least, I would call it a drop-in. For NMC, there is an issue of cross-contamination in the slurry mixing because our cathode is iron-based, but so is LFP. So there you can just do a cleaning and swap it basically. There's a slight difference in the drying protocol. We are using much less dry room environments compared to lithium. So the dry room footprint is lower, which would theoretically give a lower capex per square meter if we build a bespoke sodium-ion factory.
Okay,
I just want also to highlight that, as Johan said, that you can use any lithium-ion battery factory to produce sodium-ion batteries. So any existing. So it's, of course, you need to do the cleaning properly, but there is no bottleneck. If you start a new factory, as Johan said, it's like a copy-paste of lithium-ion battery factories. That's why we call it, this is a drop-in solution. You can use it in any type of lithium-ion batteries. The advantage, as Johan said, is that you don't need necessarily high drying steps as you need for lithium-ion batteries if you work on the solutions that we are providing via Altris. So the capex and opex will be lower for this type of sodium-ion batteries. Another big advantage is that everything is aqueous-based. You don't need NMP. So from environmental perspective, you don't. This is much better. You don't need any NMP. You don't need to capture NMP during the process and reuse it. None of those is needed. It's all water-based.
Yes, that's a very important point. And I would add also, it's not only environmentally positive, but also very much cost effective, and really saves a lot of cost throughout the process. Be having a lot of questions, maybe about the circularity. Just to have your general view on how do you face the question of the circularity. As you know, a lot of companies, especially on the downstream, might be worried about the feasibility and the economics of the recycling of the sodium-ion batteries. What's your general take on that? Are you also working in that on that aspect, or technically there is a gateway to a better recovery rates? The battery regulations, the European battery regulations is coming up, so that might be also the question is extending to a more squeezed timeline. So please.
I mean, the process is we can use the same processes as for lithium ion, but as you mentioned, I think also before, there's a question of economics here because the input materials are so cheap. So it might there's a different calculation to make the business case fly. There is no, expensive materials that we are replacing by recycled materials, but process-wise, there is nothing that prevents us from using the same equipment and infrastructure as for lithium.
Okay, thank you. I'm gonna ask a question about the slides that Reza showed in terms of the cycling and the first 1,000 cycle that you mentioned. We have a question on the capacity loss on the first cycle.
So I saw that
If
question.
you could, yeah.
The question, I would say, is not, or the statement is not correct, because the statement in the question is that all sodium-ion batteries have low first cycle Coulombic efficiency. That's not correct to generalize, because it depends very much what type of electrolyte and what type of anode you use, what is the quality. So the Coulombic efficiency in the first cycle Coulombic efficiency in those cells is above 92%. And that's not only for Altris, but also for all commercial cells that we see from China today. They all have rather high Coulombic efficiency, similar to lithium-ion batteries. The reason that maybe you don't get a high Coulombic efficiency in the lab is many of the materials that you get into research labs, unfortunately, are not pure enough, because there are too many random suppliers that you can buy materials that are not high quality. But otherwise, no, the first cycle Coulombic efficiency is as good as lithium-ion batteries.
Okay, perfect. Thank you. So one more question is about the OEMs and the automotive sector. As you might know, we have been engaged and we are collaborating with the European Commission and the automotive partners and providing a fit agenda for the automotive sector, the electric mobility in general. But also from the BEPA side, we are in charge of providing the insights of the community on the battery technologies. There, as you mentioned, Reza, the, the perception of the required batteries for the mobility was very high, or at least the standards, the perceived standards and the perceived KPIs were really high, and maybe they were a little bit over focused on some metrics and missed the others. But throughout the time, your experience with the OEMs and the automotive sector in general, is the paradigm shifting? As we know, the Commission released a set of the new guidelines for the automotive sector, and there is a new term, affordable e-car. So it has been realized at the EU level that for the better adoption of the electric mobility, we have to move to a probably the affordability matters. First of all, we need the EVs to be affordable. That's first and foremost. But also maybe one intermediate approach to that is to reduce the size of the cars to make it for the stakeholders that you're more affordable. These kind of a talking points, this paradigm has been shifting in your opinion, in your exchanges, in your interaction with them, or still we are looking for a very high energy density, if you will, batteries, and nothing but that would be satisfactory.
No, as I say, you clearly see a big shift today in automotive industry that cost has become much more important than, let's say, 10 years ago. And the major automotive industries are happy to look at low energy density lithium-ion cells, let's say LFP cells versus NMC. 10 years ago, if you would have said LFP, no one in European automotive industry would talk with you or would be interested to discuss. But today everyone is interested. So this is a big shift, which requires, there will be, at the end, there will be a trade-off between cost, energy density, or driving range, and so on. So if you go to LFP, sure, lower cost, but the driving range is probably lower than the NMC based. If that is acceptable by customers and societies, that's one way to expand EVs in society, so everyone can buy rather cheaper EV compared to more expensive EVs. Making smaller batteries, as you said, and lower energy density batteries makes batteries and EVs cheaper, but that requires also more charging stations. I mean, the most sustainable model that comes to my mind, which probably will not be there in next few years, but maybe in the future, is that we have very small cars with small batteries, limited driving range, but many more fast charging stations. It's like a gas station. You go to the charging station, you can charge your car in few minutes, then you drive. That type of limited driving range and limited capacity and limited size batteries is enough for most people in societies.
No, absolutely. I mean, the data really shows that even in China, when you have, because some people we hear that the sodium ion has been already extensively used in China. That's true, but you have to also look at the charging facility in China and the driving range. So the large deployment of the sodium ion, as you mentioned, is primarily because the size is small, and the small size comes with the other costs that should be more distributed between the governments, and that's the charging facilities. Absolutely. Maybe one last question, if you could just give us your very short answer on the there has been a lot of comparison with the LFP, and we know that the LFP, one major one major factor attributing to its better performance, if you will, was the design at the system level, and the battery pack, and the cell to pack design, etc. Again, it's mostly safer, if you will, compared to NMC, so less control system, etc. Have you worked on that? What's your take on this? Is it something, again, just like the production, something close that could be developed, or we need a new stream of the activities and research on that?
Yeah, so we have, looking at you, Reza, and you looking at me probably, but we have limited work done on the system level savings. There is some, but I think that would be a good candidate for more research focus, to be honest, on how much cost can be saved by these reduced cooling requirements and so on. So that's a very good point.
Okay, perfect. Thank you so much. Very much enjoyed your presentation. It was very informative. You are one of the few startups in Europe and companies working at that. We are very much collectively proud of your activities, and we very much look forward to your success. I hope that this progress and these results could be shared more extensively within the stakeholders, and we can really see the benefits of this very, very promising technology. So thank you, Reza. Thank you, Johan. Thank you all for joining us today. We very much looking forward to see you in our next webinars. The recording and the presentations will be shared with you. But in the meantime, I wish you a very good day, and thanks again. Bye-bye.
Thank you, and thanks everyone for listening.
Thank you, and thanks for having. And sorry that we couldn't go through all the questions, but but we can. I would be happy to answer the questions if you guys drop me email. Yeah, sorry that we
Please,
didn't.
yes, thank you so much, Reza. So
Thank you.
please contact Reza for more questions.
Thank you.
Bye-bye.
Bye.
Bye-bye.